We spend billions of dollars to reach Mars, but the reality is sobering. Physics may have already forbidden our return. It isn't a lack of technology, it is a single formula that is quite literally laughing in our faces. Humanity successfully conquered the moon 6 times. We landed people on the surface of another celestial body and brought them home safely. Today, that feels like a routine entry in a history textbook. We have grown accustomed to the idea that space is just another frontier to be tamed. Looking at the triumphs of private spaceflight, giant rockets that launch and then land back on their fins with surgical precision, we have developed a sense of inevitability. We think that Mars is simply the next logical step. The same concept, just a bit further with a bit more fuel and a slightly longer journey. It feels as though the hardest part is behind us. We have learned to live in orbit. We have mastered reusable systems. But the truth is, we are still standing at the threshold of a prison whose walls are built not of concrete, but of mathematics. The idea that Mars is just the moon on steroids is fundamentally flawed. This is not a gap you can bridge by simply building a slightly larger rocket or adding more stages. The obstacle is mathematical. It is hard-coded into a formula that knows no mercy and takes no bribes. We can get there, and we might even land successfully, but the moment the first human touches that red dust, they may realize a terrifying truth. They are the first resident of the most expensive penal colony in history, one with no evacuation plan. To understand why, we have to look at the fundamental principle of rocketry. A rocket moves by throwing mass in the opposite direction. This is Newton's third law in action. Every vessel in history, from the first firecrackers in ancient China to the starship, has obeyed this rule. But here lies the fatal nuance that engineers call the launch curse. Every drop of fuel you need at the very end of your journey, for braking at Mars, for landing, for taking off again, and for the journey back to Earth, must be carried with you from the very first second you ignite the engines at Cape Canaveral. This makes the rocket heavier at launch. To move that extra mass, you need even more energy, which means even more fuel. But that additional fuel has weight too. It too requires energy to be accelerated. It is a ruthless, suffocating spiral. Your change in velocity, known as delta V, is governed by the Tsiolkovsky equation. It tells us that the change in velocity is the exhaust velocity multiplied by the natural logarithm of the ratio of the initial mass to the final mass. This is the logarithm trap. It means the relationship between fuel mass and speed is not linear. It is exponential. If you want to double your speed, the volume of fuel required doesn't just double, it grows geometrically. Shifting from 3 to 6 kilometers per second doesn't double the load, it triples your mass ratio. When you reach the speeds necessary for interplanetary travel, 95% of the rocket's weight is nothing but fuel. The thin aluminum hull of the rocket is merely a fragile vessel for a colossal ocean of explosive liquid. Engineers call this the tyranny of the rocket equation. Imagine a long car trip across a vast desert with no gas stations. You have to carry all your fuel with you, but gasoline is heavy. To carry the extra cans in the trunk, your engine burns more fuel. You end up needing more fuel just to carry the fuel that was supposed to get you home. At a certain point, you hit a wall. Adding another gallon of gas provides almost zero benefit because all its energy is spent just moving its own weight. You reach a point of diminishing returns where you're burning fuel simply to transport more fuel. This is the dead end facing modern astronautics. Consider the Saturn V, the greatest engineering feat of the 20th century. At launch, that rocket was 85% fuel. Its total mass was 3,000 tons, the weight of a naval destroyer. But the most shocking part, the piece that eventually returned to Earth with 3 astronauts weighed less than 13 tons. That is less than 1% of the original weight. Everything else, thousands of tons of metal, engines, and tanks, was just a delivery system for that tiny module. The entire Apollo program was a desperate, calculated fight to shed mass as quickly as possible. The lunar module was flimsy, almost paper thin by engineering standards, because the moon's gravity is 6 times weaker than Earth's, and it has no atmosphere. You don't need aerodynamic fairings or heavy heat shields to take off from the moon. Half the ship, the landing platform, was simply left behind as junk to save every possible gram for the return trip. The total velocity budget for the Apollo missions was roughly 15 to 16 kilometers per second. The Saturn V achieved this at the absolute limit of what physical materials and chemical energy can withstand. Now let's look at Mars. The first thing that catches you off guard is the sheer scale. The moon is 380,000 kilometers away, a 3-day trip. If something goes wrong, the crew has a chance to swing around the moon and get back alive. Mars is hundreds of times further. Even at their closest approach, we are separated by 55 million kilometers. To cross this abyss, you have to time your launch perfectly. This window opens only once every 26 months. You travel along an arc for 8 or 9 months. Think about that, 9 months in deep space. No U-turns. Once you leave Earth's orbit and burn your departure stage, there is no going back. You are locked in a steel capsule in the middle of a frozen void. If a leak develops in the air filtration system or a stray cosmic particle fries the navigation computer, you are on your own. Help is 9 months behind you, and the next safe harbor is 9 months ahead. There is no Coast Guard in the void. In space, distance isn't measured in kilometers, it's measured in energy. To enter orbit around the red planet, you have to brake, another fuel expense you've been dragging from Earth. Then begins the descent. And here, Mars reveals its most treacherous trait. It has an atmosphere, but it is the quote unquote worst of both worlds. Its density is only 1% of Earth's. Being on the surface of Mars is like being 35 kilometers above the Earth. It's just enough atmosphere that you can't ignore it. You need a massive heavy heat shield or you'll burn up in seconds. But it is far too thin to stop you effectively. On Earth, massive parachutes can gently lower heavy cargo. On Mars, a parachute can only slow a heavy ship down to about 320 kilometers per hour. Imagine hitting a brick wall in a racing car. That is what a parachute landing on Mars looks like. For a 1-ton robot like Curiosity, engineers used a quote-unquote sky crane, a rocket-powered platform that lowered the rover on cables. But for a human mission, which would weigh between 20 and 40 tons, that trick won't work. You would need a parachute the size of a stadium, and the Martian winds would tear it to shreds before it even inflated. The only way down is to use rocket engines to brake almost the entire way to the ground. And every gram of that descent fuel is weight you had to fight to get off Earth in the first place. NASA estimates that for every 1 ton of cargo we want to land softly on Mars, we need to launch 20 tons into Earth's orbit. This ratio should be terrifying to any dreamer. It means to land a house-sized habitat, you need to launch a fleet of rockets. Let's assume a miracle happens. The engineers are brilliant, the landing is soft, and the crew is standing on the surface. They are heroes, icons of a new age. But the moment comes when the mission is over and it's time to go home. This is where physics begins to mock our ambitions. Leaving Mars is arguably harder than getting there. Yes, the gravity is lower, 38% of Earth's, but you are no longer at a spaceport in Florida with factories, supply chains, and thousands of engineers behind you. You are on a barren, frozen rock, millions of kilometers from the nearest repair shop, and you need to launch a full-scale heavy rocket. To blast off and head for Earth, you need a velocity of about 7 kilometers per second. Calculations show that a 10-ton return craft would require about 35 tons of fuel on the Martian surface. Think about that, 35 tons of explosive, cryogenic propellant on a planet with no gas stations. If you try to bring that fuel from Earth, the starting mass of your rocket at Cape Canaveral would grow so large that no launch pad on Earth could support it. The rocket would be so massive it would collapse under its own weight before the engines even ignited. The mass multiplication factor is staggering. To get 1 kilogram of return fuel to Mars, you have to burn hundreds of kilograms at launch. The total velocity budget for a round trip to Mars is around 22 kilometers per second. For context, that is nearly 1.5 times what was needed for the moon. But the logarithmic scale of physics is heartless. That 7 kilometer per second difference can mean a 10-fold increase in the starting weight of the entire system. A round trip using only Earth-brought fuel would require assembling a ship in orbit weighing tens of thousands of tons. The International Space Station weighs 450 tons. We would need to build 50 such structures, fill them with fuel, and send them off. No one in their right mind considers this feasible in the near future. Even with infinite fuel, you don't have infinite time. Planets are not static points. They are runners on a circular track moving at different speeds. The return window to Earth only opens once every 780 days, roughly 26 months. You can't just say, okay, we're done, let's head back. Orbital mechanics force you to stay on the surface for about 500 days, nearly a year and a half on a hostile planet. This isn't a choice, it's a dictatorship of orbital trajectories. The entire voyage will take at least 3 years. And for those 3 years, the human body will be in conditions it was never evolved to handle. Mars is a radiation hell. Unlike Earth, it has no global magnetic field to deflect solar winds and no thick atmospheric shield. Cosmic rays, high energy particles moving at near light speed, pass through aluminum hulls as if they weren't there. They stitch through human tissue, shattering DNA and causing radiation sickness. Over a 3-year mission, the radiation dose will likely exceed all safety limits. The only way to truly protect the crew is to surround the living quarters with a meter-thick layer of lead or several meters of water. But remember the rocket equation? You can't carry that, it's too heavy. They will live in a module the size of a few shipping containers. If a pump in the water recycling system breaks, you will be drinking your own processed urine until you figure out how to fix it with duct tape and a 3D printer. If someone gets sick or injured on the surface, there is no hospital, there is no evacuation. The nearest ER is 9 months away. Psychologists warn this is the ultimate test of the human mind. 4 to 6 people trapped in a tiny space for 1,000 days. The realization that Earth is just a tiny blue dot that you cannot reach can break a person's spirit. The 20-minute communication delay means you can't even have a real-time conversation with your family. Hello, and a 40-minute wait for the response. This is loneliness on a scale we cannot fathom. Every word you speak is ancient history by the time it reaches home. To escape this dead end, scientists have proposed in situ resource utilization, or ISRU. Why bring fuel if you can manufacture it there? The Martian atmosphere is 95% carbon dioxide. Using the Sabatier reaction, we can combine that gas with hydrogen to create methane and oxygen. This chemical reaction requires a catalyst and heat, but it produces rocket fuel. Methane and oxygen make for excellent rocket propellant. In theory, it's brilliant. You skip the need to haul 35 tons of fuel through the rocket equation. Instead, you send an autonomous chemical plant ahead of time. It lands, deploys solar panels, and for a year, it slowly fills the return rocket's tanks. But let's be honest, we have never manufactured fuel on another planet. This would have to be a completely autonomous factory working perfectly in the middle of dust storms that can last for months. Martian dust is a fine, statically charged abrasive that gets into every seal. If a valve jams, the mission fails. If the crew arrives and finds that a software glitch left the tanks only half full, they are doomed. They would be standing next to a useless rocket, watching their oxygen supplies tick down. Each of these challenges is a generation-defining hurdle. When combined, they create a barrier that makes Columbus's voyage across the Atlantic look like a walk in the park. I am not saying a Mars mission is impossible. Humanity has always found a way to cheat the rules. Perhaps we will use nuclear thermal rockets, which are twice as efficient as chemical ones, or orbital refueling stations filled over years of preparation. But we have to stop treating this like a viral social media event. Mars is a crucible. The rocket equation guarantees that every mistake is magnified 100 times. It forces us to choose. Either we build a fleet the size of a city, or we learn to live entirely off the land of another world from day one. Both paths are at the absolute edge of our current capabilities. This is the true problem with returning from Mars. It is not enough to reach it and claim a triumph. You must have the mathematical right to come home. And right now, the universe is making it very clear we are still too heavy for this journey. Perhaps the first Martians will be those who decide ahead of time never to return. Those who make the red planet their new home, not out of romance, but because physics simply left them no other choice. Do you believe we are ready as a species to send people on a mission where the chance of returning home is less than 50%? Is the risk of becoming a multi-planetary civilization worth it? Or should we stick to robots until we finally crack the tyranny of the rocket equation? Write your thoughts in the comments. This is one of those topics where a single correct answer doesn't exist yet. Subscribe to the channel to join us as we explore the limits of the possible in this indifferent yet breathtaking universe.